Hey everyone, in this mini lecture we're going to look at the area of logarithmic differentiation. So sometimes when looking at a function we go to differentiate it. It can be a really complex looking function, something really challenging to differentiate with all of the basic rules that we know. So this is where we can apply logarithmic differentiation. So here we're told to differentiate y equals x to the x power. So we're going to apply logarithmic differentiation. So the first step is to take the natural log of both sides. So we take the natural log of y, and that's equal to the natural log of x to the x power. So this is where you have to refresh your memory and look at the properties of logarithms that you've studied before, right? So one property tells you that when you have an exponent, right? You have the logarithm of something and it's raised to an exponent, then that property tells you that you can bring that up to the front as a coefficient. So it becomes x times the natural log of x, right? So that exponent comes to the very front as a coefficient. Our third step will be to actually differentiate both sides with respect to x. Right? Differentiate both sides with respect to x. So we'll do this implicitly. So we have to say what's the derivative of the natural log of y. Well, in using implicit differentiation, we're taught we use that chain rule to take the derivative of the outer, which is the natural log of that something, which is the derivative will get us 1 over y. We keep the inner the same. And then it's multiplied times the derivative of the inner, where we were told that the derivative of y with respect to x is just that, dy dx. Okay, so now we have to take the derivative of the other side. Okay, so in taking the derivative of this side right here, it looks like we have one function times another function, so we'll have to apply the product rule. The product rule says to take the derivative of the first function times the second function, add that to the first function times the derivative of the second function. So we apply the product rule. So the derivative of x is just 1 times the second function, which is the natural log of x. We're to add that to the derivative, to the first function, which is x, times the derivative of the second. The derivative of the natural log of x is 1 over x. All right, so I'm just going to clean it up a little bit. I'll say 1 over y dy dx is equal to 1 times the natural log of x is the natural log of x, and x times 1 over x makes x over x, which is just going to be 1. All right, so now the final step is to solve for dy dx, get dy dx by itself. So to get dy dx by itself, it's just algebra, right? We can divide both sides by that 1 over y, or in essence, to do the same thing, we can just say let's multiply that other side by y, the reciprocal of 1 over y. So we have y times 1 plus the natural log of x. All right, no change there. All I did was move the 1 to the front before the natural log of x. All right, and then lastly, we can say to ourselves, okay, let's substitute for that y. What was the y? Well, if you go back to the original problem, then you'll see that the y was x to the x power. And then this is times the quantity of 1 plus the natural log of x. All right, let's take a look at our next example. It says to differentiate y is equal to x squared times the quantity of x minus 1 times the quantity of x squared plus 4 raised to the third power. Okay, so sometimes, again, we see things that can look a bit complicated, right? So we would maybe want to use a strategy that will simplify things, and that strategy would be what we're doing, logarithmic differentiation. So here, we're going to take the natural logarithm on both sides. So the natural logarithm of y And then I'm just going to take the natural log of this entire side. So the natural log of x squared times the x minus 1 times x squared plus 4 cubed. All right, so then the natural log of y is still on the left, but now again, think back, refer back to your properties of logarithms, right? So we have a single logarithm. We can actually convert this to multiple logarithms, right, with the same base. I think if we use a specific rule, right, a product rule, we can convert these to sums of logarithms. So we should have the natural log of x to the second power plus the natural log of x minus 1 plus the natural log of x squared plus 4 to the third power, right? Remember that? So if you have products, a single logarithm that's a product, then you can change it to multiple logarithms and sum them up. All right, so in our next step, I'll bring down the natural logarithm of y. So here we have the natural log of x to the second power. So remember, there's another property. We used it just in that last example where the exponent can come to the front of the logarithm. So we have 2 times the natural log of x plus the natural log of x minus 1. And here we can use that property again, plus 3 times the natural log of x squared plus 4. All right, so we have the natural log of y is equal to all of those logarithms on the right-hand side. So now we can go on to our next step. So our first step was to take the log of both sides, and then we applied the properties as needed. The next step is to find the derivative of each one of those. So we're going to find the derivative with respect to x. So dy dx, natural log of y, right? So dy dx, natural log of y, I'm sorry, it should say d dx. And then I'm going to take the derivative with respect to x of everything else over here too. So I'm just going to put all of this in brackets just to show that I'm taking the derivative of everything. But I'll do them individually. So natural log of x plus natural log of x minus 1 plus 3 natural log of x squared plus 4. Right, just to show that I am doing that next step of taking the derivative with respect to x. All right, so the derivative with respect to x of the natural log of y. So we use our implicit differentiation. We say to ourselves using chain rule, we take the derivative of the outer, which is 1 over that y, the inner stays the same, times the derivative of the inner. Well, the derivative of y with respect to x is dy dx. All right, so now the derivative of 2 times the natural log of x. Well, the natural log of x, its derivative is 1 over x, right? 1 over x. So what is 2 times 1 over x? It's just going to be 2 over x. All right, and now in this part, the derivative of the natural log of x minus 1, the natural log of x minus 1. So we apply the chain rule. So the derivative of the outer is 1 over x minus 1. And then we multiply it times the inner. Well, what's the inner? It's derivative. The derivative of x is just 1. Derivative of negative 1 is just going to be 0. So then we have 1 over x minus 1 times 1. Right? So we have 1 over x minus 1. And now taking this next piece right there, we have a 3 times whatever we're going to do. So we're taking the derivative of that, but the 3 can come out as a coefficient and be multiplied after we find the derivative of the natural log of x squared plus 4. So we can apply the chain rule here. So the derivative of the natural log of x squared plus 4 is 1 over x squared plus 4, right? The derivative of the outer, keeping the inner the same, times the derivative of the inner. Derivative of the inner, which is x squared, is 2x. Derivative of 4 is 0. So 2x times this 1 over x squared plus 4 is 2x over x squared plus 4. And then times 3, what do we get? 6x over x squared plus 4. All right, and then lastly, we can solve for dy dx. So in solving for dy dx, then we're going to either say to ourselves, hey, let's divide both sides by 1 over y, or just multiply by its reciprocal, which is y. So I'm going to say y times 2 over x plus 1 over x minus 1 plus 6x over x squared plus 4. And then lastly, I can go ahead and substitute in for that y. So dy dx is equal to, what was y? Well, y was what we had in our original question. So y is x squared times x minus 1 times x squared plus 4 cubed times 2 over x plus 1 over x minus 1 plus that 6x over x squared plus 4. All right, and that is our derivative.